anyway.
I will start. Good day, and here in Charlotte is the morning, beautiful early spring morning, and my talk will be about localization theory. Localization theory for two types of the random Schrödinger operators. I will give in the very beginning some short review of the localization theory, and after this I will discuss localization theory for the fractal lattices, and the typical example is Sierpinski lattice. This is a lattice which dimension is less than 2 and greater than 1, spectral dimension or Hausdorff dimension, and such graphs demonstrate some similarities with one-dimensional theory, which is well known. And the second part of my talk, but I believe that I will continue this talk in next month. Next month I will be in Newton Institute. In April, I expect to spend the time from April 1st until the beginning of May. And I will give some mini course on the spectral theory of the fractals. This is the topic of our recent joint studies with Alexander Grigoryan and Alexander Bendikov. But second topic, possible topic, is localization theorem for the hierarchical Schrödinger operator related to periodic analysis. And I'm not sure that I will be able to start today this topic. Let us begin. I doing my talk from the house because situation with COVID still in Charlotte is very bad, and university right now we have no regular classes. Okay. This is my whiteboard, and let us start. The very first and well-known result in the localization theory is one-dimensional localization. Assume that we have lattice U1 and we have Hamiltonian delta plus V of x omega, and delta is a lattice Laplace operator, delta psi of x. X is a point on the lattice, is psi of x plus 1 plus psi of x minus 1. Spectrum of Laplace operator is the interval from -1 to +1, and we perturb, and this spectrum is actually continuous, and we perturb this Laplace operator by the random potential V of x omega are IID random variables, and we will assume that they are good enough. For instance, they have bounded continuous density of the distribution P of V. Then this operator is well defined. It's self-adjoint in lattice U1. It's unbounded if the random variables are unbounded. For instance, if the random variables are Gaussian. And well-known results of Kuntz and Suyar. It was end of 70s, beginning of the activity in this area. But mathematical activity, of course, physicists, Mott, Anderson, and others studied in 60s already similar objects. But Kuntz and Suyar proved that P almost surely this operator H has the dense point spectrum. There are lambda I of omega corresponding eigenfunction psi of x and omega, which belongs to L2 on the lattice U1, and they form complete orthonormal basis in L2. But in contrast to the discrete spectrum, set of the eigenvalues is dense on some interval. And this is exactly the spectrum of the operator H. And this spectrum is the sum of the interval minus 1 plus 1, that is spectrum of Laplacian. And this we algebraically must add here support of the density P. This is description of the spectrum as I said, and eigen function in this case are decreasing exponentially. The proof of Kuntz-Suyar theorem, as well as the proof of the corresponding continuous theorem for continuous Schrödinger operator on the real line. This is our old paper with Goldschmidt and Pasteur. Both proofs were based on the Furstenberg theorem. It was possible to cite a monodromy operator for this Hamiltonian and prove that there are almost surely positive of exponent, and it gave finally, after some tricks, that so-called exponential localization. We have dense point spectrum on some interval, and corresponding eigenfunction are decreasing very fast. When many years ago, at the end of 60s or maybe beginning of 70s, when I gave talk about such kind of the topic on the seminar by Boris Moiseyevich Levitan in Moscow State University. Levitan was together with Marchenko and Gelfand leading specialists in the spectral series at that time. And when I discussed this pure point spectrum, Levitan said that I do not understand what is the mechanism. There are some mathematical tricks, but why the spectrum must be pure point? Why we have no, for instance, for the bounded potential, why we have no waves here? Why we have no absolute continuous spectrum? He said that I understand also that there are continuous but no way differentiable functions, for instance, trajectories of the linear process, but this, however, such function outside my intuition. And I agree that proof is corresponding theorem in our old papers with Goldschmidt Pasteur or in Kuntz-Suyar, that it was pure mathematics. The first result, which from my point of view gave explanation why we have some strange spectrum in situations. This was result theorem by Simon and Spencer. It was probably 1989. And this is the following theorem. Let us consider non-random operator as let's h is equal to delta plus v of x, and assume that potential v of x is unbounded. It's unbounded near plus infinity and near minus infinity. Assume that lim sub of absolute value v of x, if x goes to plus infinity, equal to plus infinity, and if it goes to minus infinity, is also plus infinity. It's unbounded. The sign of potential is not important here because delta is a bounded operator. In continuous case, of course, this unbounded is necessary to understand correctly. There is version of this theorem for continuous case, but which I will not discuss. And then, in this case, spectrum, absolute continuous spectrum of the operator H is empty. Spectrum is singular continuous. And the proof, which is relatively simple, gives the following physical interpretation of this result. I will demonstrate this interpretation in the following situation. Assume that we have, again, for instance, half axis. There is no big difference between half axis case, full axis case, and assume that potential v of x is summation h sub n delta of x minus xn. Potential is supported on some point xn, and for instance, positive. This height of this bump is h sub n. But at the point here, we have boundary condition cosine theta naught times psi at the point 0 minus sinus theta naught psi at the point -1 is equal to 0. And this theta naught we call boundary phase. It's some angle on the interval 0 pi. And assume that Hn goes to infinity, and Hn, which is much more essential, goes to plus. This is unbounded potential on the right direction. What we want to understand how the quantum particle propagates through the system of the barriers. This xn minus 1, Hn minus 1. Assume that it's quantum particle at some moment between two successive bumps. Bumps are very high, and as a result, propagation of particles through such bump has very small probability. Very long time it's oscillate between two bumps, but due to tunneling effect, sooner or later particle will leave this interval. But because Hn is greater than Hn minus 1, with probability greater than 1/2, but if Hn significantly higher than H minus 1 with probability close to 1, it will leave interval in the left direction. It means that for the quantum particle, of course, it's not classical Markov chain, but at the level of physical intuition for the quantum particle, we have drift in the left direction. And if this drift is sufficiently strong, then we will have here for each given admissible energy lambda, we have here invariant distribution from which belongs to L1 as a result belongs to L2. And this invariant distribution will be exactly due to standard interpretation of quantum mechanics will be our eigenfunction. If Hn increasing slowly to infinity or distance between point xn is growing extremely fast, then in this case we can expect we can expect a singular continuous spectrum. But wave propagation, when quantum particle more or less with a constant speed goes to infinity, like we have in the case of sinusoidal wave, something like this, such kind of behavior is not possible. This is Simon-Spencer result. At the same time, close to this time, maybe beginning of 90s, we published with Kirsch, Molchanov, and Pastur, some version of the Simon-Spencer theorem, which contains not only statement about absolute continuous spectrum, but which contains statement about a pure point spectrum. We have this is the following theorem that, again, I will formulate this theorem in particular case of the model which I formulated several minutes ago. It, in fact, is more general, but for better understanding, I consider exactly the same model. We have xn. At the point xn, we have one hn. We assume that now that hn goes to infinity sufficiently apart, namely the summation 1 over epsilon of hn is finite. And but at the point 0, we have boundary condition with phase theta naught. And assume that point xn and as goes to infinity not too fast, slower than exponentially, or at most exponentially. Xn smaller or equal than c to the power n, where c is some constant which is greater than 1. Then, in this case, there is a theorem that there is no probability here. This is a pure deterministic situation. Almost everywhere in the theta naught, for almost all in the sense of Lebesgue measure of the boundary condition theta naught, spectrum or spectral measure of operator H is pure point. No, in this case, we cannot guarantee that eigenfunctions are decreasing exponentially. It depends on the distribution of point xn and also on how fast hn goes to infinity. But in all cases, spectrum is pure point. And this spectrum is dense on the zero infinity. Spectrum as a set is zero infinity. We will assume, of course, that xn minus xn plus xn minus 1 tends to infinity. 3 conditions. Pure deterministic situation. And remarkably, that there were many attempts to prove that this is true not for almost all theta naught, but for all boundary phases. But Alex Gordon more or less the same time, a bit later, he proved a remarkable result that there exists set gamma belongs to the interval 0 pi. Set of possible values of the boundary phase theta naught such that that measure, the Lebesgue measure of gamma is equal to 0. But this gamma, the G delta set, it's topologically generic set. And if theta naught belongs to gamma, then for the same potential, there is no eigen values at all. Spectrum is pure singular continuous. Spectral measure of H is singular continuous. Everything depends on the one-dimensional randomness, so on the boundary phase. It demonstrates instability of exponential of the localization. In probabilistic situation, if you have random potential, then in this case, our statement is that with probability 1, we have exponential localization. But this is a deterministic case. Hn is not random, Xn are not random, that only parameter, continuous parameter here is the theta naught. For almost theta naught, we have, I repeat, third time, pure point spectrum, dense pure point spectrum, which eigenvalues covers densely interval from 0 to infinity. But for some topologically generic set gamma of the theta, possible values of the theta naught, we have singular continuous spectrum. And what is very important in this theorem, as well as the Simon-Spencer theorem, is the fact that we have increasing system of barriers, and our quantum particle cannot avoid such barriers. If you consider, for instance, lattice Z2, and let us consider on the lattice Z2 very similar operator, delta H equal H psi equal delta psi. Delta psi is summation over 4 nearest neighbors plus V of x omega. And V of x omega, for instance, are normally distributed with parameters 0, 1, unbounded random variables. Then we have the following situation. Delta is bounded. Let us consider set of x's for which V of x is large, greater than some m. This set is infinite, of course, but this set contains density of this set is small. Probability that V of x greater than m, this probability is epsilon of m, it tends to 0. You can find, of course, precise asymptotic. But what is important here is that high values of the potential cannot cannot form the connected set. They cannot stop propagation of the quantum particle to infinity. It simply can move between such more or less sparse points when potential is very large. It means simply that a set of x's, for instance, potential of x is greater than m. This set of x's in one-dimensional case contains isolated finite islands. It's union of some islands I, some I, and all such islands are finite. It's exactly high peaks, which I discussed earlier, are the boundary point of such islands. But in two-dimensional or in multi-dimensional case, this set is not percolate to infinity. This set contains only finite islands, but outside this island, we have some isolated islands, and quantum particle can move to infinity oscillating between such islands. This is one-dimensional lattice is non-percolating graph. Z1 1 is not a percolating graph. And I want now to discuss class of non-percolating graphs and prove and explain why in this class of the graphs spectral situation is similar to dimension 1. What is the simplest example of non-percolating graph which is not Z1? This is so-called Sierpinski lattice. One of the is the simplest fractal lattices. Sierpinski lattice is closely related to so-called Sierpinski gasket, which is a continuous fractal. This is some skeleton of the Sierpinski gasket. Construction of Sierpinski lattice is very simple. We start from some triangle. We equilibrium triangle, we divide by midline this triangle on the 4 equal triangles, and after this we continue our construction, something like this. But again, we are doing one more triangle and construct a bigger triangle above. This is what is important in this construction. First of all, each point on this graph, this is the edges of the graph, and each triangle has, small triangle has 6 vertices, basic triangle. But let's consider one particular point. This point has 4 nearest neighbors, which are shown here. I will use here black color. This is my point X, and we have point X prime. 4 nearest point X prime, except initial point, this origin of Sierpinski lattice, which has 2 neighbors. But delta psi of X, like in one dimension, is equal to summation psi of X prime, where point X prime are closest neighbors of the given point X. This is a local operator, and very similar to lattice 1-dimensional, 2-dimensional lattice Laplace operator. This is, of course, bounded operator. But Sierpinski lattice has the following very important property. In Sierpinski lattice, there are points, pair of the points, which separate infinity in neighborhood of the point O. O is the origin. Let us consider this point and that one. That's if, for instance, we start random walk on this lattice with continuous time when we jump with equal rates to the nearest neighbors, then its random walk cannot avoid such pair of the points. Another pair of the points is shown here. Next pair of the points will be here. There are finite sets containing each only 2 points, which separate Sierpinski lattice on the disjoint blocks. In one dimension, each point divides lattice Z1 on the left part and right part. But here we need pairs of the points. Let us assume that we consider field of the Bernoulli field of the lattice ZD such that for an probability of psi of x is equal to 1 is equal to p, probability that psi of x is equal to 0 is equal q, that is 1 minus p. And assume that p is very small, smaller than epsilon, some very small epsilon. But sorry, it's q, which is 1 minus p. Then in this case, it will be this 1 minus epsilon. Concentration of the points 1 is very small, arbitrarily small. But probability that in 2 points separated successive blocks we have 2 ones, this probability will be epsilon squared. Probability that along this line separating successive blocks we have here 1 and here 1, this probability is epsilon squared. Of course, this probability is small, but we have infinitely many such pairs, and it means that there are infinitely many situations when we have 1 and 1 on such separating pair of the points. It means that zeros, concentration of the zeros is very close to 1, but zeros cannot propagate to infinity. Set of the zeros on this random Bernoulli field it always contains finite connected sets. Finite connected sets separated by this such pair of the point when value of psi is equal to 1. This is non-percolating graph. It can be symbolically presented in the more general form. Assuming that arbitrary graph which contains some sets, some blocks. Inside this block, we have arbitrary structure of the connections, but we will assume that number of the nearest neighbors is bounded. It means that operator delta is bounded in all such clusters or blocks B1, B2, B3, Z3, and so on and so forth. But blocks are connected only, for instance, by 2 or 3 one-dimensional intervals, or maybe simply such intervals can be equal to 1 point. We can consider such situation, and so on and so forth. In this case, 1 common point for 2 neighbor blocks. Or maybe consider this case when we have 2 or 3 points. But what is important here is that we have finitely many possible connections between blocks. And if we consider V of x omega, it's again, if you consider potential, if we consider operator delta plus V of x omega, value of x are Gaussian random variables or Cauchy or something like this, but I want to consider unbounded random variables. Then there are necessarily infinitely infinity many pairs of the point, when potential of x will be very large, something like this. Using Borel-Cantelli lemma, you can prove that big values of potential of x will separate blocks. This is, and it means that for small values of potential, the set where potential V is not very large, this set can be divided on the finite connected component. We have disjoint cluster when potential is not very large, separated by very sparse pairs of the point when the potential of x is very large. It's picture similar to the what was in our paper with Kirsch and Pasteur. But of course, it's much more general. This is, in some sense, quasi one-dimensional situation. We have here many blocks. Blocks can be very large, but we have small number of the connections between such blocks. This is the situation number one. This situation number two, which is exactly similar to situation in the Sierpinski lattice. That's there is a huge class of the lattices which have as a following size. This so-called nested fractal. Sierpinski lattice is a simple example of nested cluster. But we can consider also even multi-dimensional lattices. We can construct Sierpinski type lattice using, instead of triangle, tetrahedron, something like this. And again, using this tetrahedron, we can construct around some new system of tetrahedron and so on and so forth. And it will be Sierpinski type lattice, which is embedded in three-dimensional space. But all such lattices, nested fractals, have this property which I formulated above, that we have here system of the finitely many points which separate successive blocks. Point when potential is large, has large absolute value. Such points have very small concentration, but nevertheless, due to very poor connection between blocks, this small concentration of large values is sufficient to separate successive blocks by the high barriers. This is the mechanism which we discuss in our paper. Which we discuss above. Mechanism which connected to Simon-Spencer theorem and our paper with Kirsch and Pasteur. And I want to formulate now the theorems. I will formulate theorems for the Sierpinski lattice. That's Sierpinski lattice. We have here operator H, which is delta plus U of x omega. I can write down, if you wish, sigma, coupling constant. But in case of Sierpinski lattice, is not necessarily. Assume that random variables v of x omega are unbounded. Assume that probability that v of x greater than m is positive for any m. We have unbounded random variables Gaussian or exponential, something like this. Theorem 1, that the spectrum of this operator H, I'm talking about spectrum as a set. It's like in all similar situation is the algebraic sum of the spectrum of Laplace operator, which is not interval here. This is a special type of the counter set, which I don't want to discuss in details. This is the counter set of the Lebesgue measure 0, and for this counter set, there is description, a lot of publications about spectrum of Laplace operator. But I'm talking not about Laplace operator, discrete Laplace operator, but about Schrödinger type operator. And algebraic sum with support of the plot and density P of V. We assume that the random variables have density and so on and so forth, or maybe sigma times P of V. And this is trivial statement, but and this spectral measures spectral measure of H is singular. P almost surely. We have independent identity distributed unbounded random variables, more or less. The NH is not important, and as I explained you before, there are points where potential is very large, and such pair of the points separate Sierpinski lattice from the finite blocks, and after this follows more or less analysis from Simon and Spencer. We can prove result. This result is very general. Theorem 2, that unfortunately this theorem is not complete. I want to formulate theorem similar to our result with Kirsch and Pasteur, that if we have some peaks which satisfy some conditions, that they increase sufficiently fast, that we have pure point spectrum. We can pure point spectrum if the values of the potential as which separate blocks are sufficiently high. That is, and this theorem already not very simple, that if probability that V of x greater than m, greater equivalent some constant over m to some power beta, and the beta must be greater than 1. Then in this case, for any sigma, we have pure point spectrum. Because blocks separated, that's pair of the large values of potential separated successive blocks must big values must be high enough. In our paper with Kirsch Pasteur, the assumption was a summation 1 over h of n must be finite. This is something like this. I believe 100% And several years ago, I tried to prove more general theorems that this is true for arbitrary random variables with continuous density. This is definitely true, and it's closely related to the physical in conjecture that in the case when the random walk on the some lattice is recurrent, but random walk on Sierpinski lattice is recurrent, as well as the all nested fractals. Then in this case, we must have localization for arbitrary coupling constants. This is what Anderson wrote many years ago in famous physical publications. This is, of course, sufficient condition, but unfortunately, we have a very strong condition. This it's Cauchy distribution is here, but not Gauss. Tails are very heavy, but I believe that I want now to finish this proof, and I believe that everything will be okay in the nearest future. But right now, I can formulate result only on such form. And I want to, in remaining more or less 15 minutes, I will try to not to give the sketch of the proof, but I want to describe several essential ingredients of this proof. And first ingredient is a representation of the resolvent. And lambda of xy is h minus lambda -1. Let us consider on our lattice our operator h, which is delta plus v. I will not write on sigma v. And this is a matrix of corresponding inverse operator. But I will assume that in the very beginning case when imaginary part of lambda is greater than 0, not simply greater than 0, but imaginary part of lambda for is greater than 4. I want to work far enough in the complex plane when resolvent is a bounded operator. This resolvent we want to present in the form of Feynman integral. Feynman introduced representation of resolvent of the classical Schrödinger operator on the three-dimensional space, for instance, as integral over some complex valued measure. Unfortunately, this is a formal representation, is not correct. There is no such measure. But in the case when Laplace operator is bounded, the situation is much better. And there is the following representation that I can write down Feynman integral R lambda of xy is a summation over all paths gamma which goes from point x to the point y. X and y are the point on our graph on Sierpinski lattice, but it's not important. This you can consider arbitrary a graph with only condition. What does it mean gamma? Gamma is a path which contains initial point, next point x1, point x2, and finally, after finally many step, point y. But x1 must be closest neighbors of the x, x2 might be closest neighbors of the x1, and so on and so forth. This is you can consider as a trajectory of the random walk, if you wish. We jump from each point to one of the nearest neighbors. And now I must consider product over all point z, which belongs to path gamma. Path gamma is a trajectory, contains, as I explained you, finitely many on point 1 over lambda minus v of z. If lambda is real, that this ratio 1 minus lambda v of z can be very large. We have here strong singularities. But if we far enough from the real axis, if lambda far enough from the real axis, we have such representation. This is path representation of the resolvent in the complex plane. It's very similar to representation of the some functional of the random walk in terms of the summation of over trajectories. The difference here is that when we are talking about, for instance, Cauchy-Feynman formula in the theory of random walks, then our functional is very regular, very bounded, usually bounded. But here we have for real lambda strong singularity. However, far enough, deep enough in the complex plane, everything is okay. This is a very important ingredient. In the case of the Cauchy-Feynman representation,
it is 10 minutes to 3 in order to organize your final part.
Okay, I understand. And using this path representation and using a strong Markov property, when we can move it from gamma, from point X, remember that everything is indicated on the blocks, but if point X here and point 1 is here, and we have blocks 1, 2, and 3, then we can classify paths. Paths from X to 1 can go directly from 1 to 2, from 2 to 3, or from 1 to 2, from 2 to 1, and blah, 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 blah. We can classify gamma on the, in terms of the successive blocks which path gamma must go through, and this will give so-called cluster expansion of the resolvent. What is second very important ingredient is the Kolmogorov lemma, and this probably very last sentence which I can say today. Kolmogorov. This lemma was in one of the early work by Kolmogorov about the early Fourier series. This is assumes that we have a summation Cn over lambda minus lambda n, and from 1 to n capital. And this is the sum of C n squared is equal to 1. Resolvent in each finite block can be presented in such a form. Lambda n eigenvalues in the block. The measure of lambda for each this meromorphic function greater than n, let's say it was some constant, which can be effectively calculated, divided by n. It means that when our parameter lambda in cluster expansion with approaches to real axis, of course, we have here small denominators. Lambda minus lambda n can be close to zero, and as a result, our resolution can be very large. But nevertheless, this singularity is not very strong. This estimation, like Kolmogorov-Arnold-Moser theory, is estimation of the small denominators. And finally, because potential is very large between blocks, we have estimation something like this 1 over hn minus lambda. Hn is very large. We have successive block containing small denominators, which are not very strong, but 1 over hn, if hn goes to infinity very fast, is very small. And after this, we have competition between two different mechanisms and so on. Anyway, I expect, as I said you in the very beginning, to spend 1 month in Newton Institute in April, and I will give mini course about 6 or 7 lectures about spectral theory of the fractals, and I will discuss, first of all, the fractals of the Sierpinski lattice type, and also hierarchical Schrödinger operator. This is already unbounded. This, in some sense, Laplace operator is unbounded. It's close to the continuous case, and it's interesting that we have in this part complete contradiction to the physical expectation. This is our recent work with Gregorian and Bendikov, and what I presented today, this is our joint work with my student Lukun Zend. And this is a journal of spectral theory, and it's 2017. It's really recent paper, and now in progress there is paper containing extension of this old paper. I want to stop today. It's exactly, my time is over, and thank you for attention.
Thank you very much for this first look.
I speak?
Yes, please.
I've written a paper, a review paper in a conference at ANS about manual calculus. It's the right name, I think. Application manual calculus is took the review. You know, Aida Kusioka-Strouk, it is very similar to our paper with Belarus. And so, in our conference, Kusioka was there, and I organized by Professor Albeverio. I've done a review paper about pathological behavior of each kernel of diagonals, and Kusioka was there, you know. And Aida Kusioka-Strouk, it is very similar to our paper with Belarus. Now I speak. Sorry about my state there.
Okay.
Okay. Are there other comments?
This is a comment because some paper enters stupid polemic. Under the time of Professor Meyer, they were not stupid polemic because Professor Meyer was in fact the Fox space.
But I didn't understand what is the.
No, you mentioned some. I done some commentaries.
I wrote a lot of paper myself with Belarus, and
yes.
But it's learned papers about spectral theory. It's mainly
I never
papers about maybe intermittency or something like this, and this is also very interesting topic. And this topic is related to this localization theory, but I don't want. I have no time to discuss this today. But then I will be in April in Newton Institute. I will be happy to discuss with everybody. I have had no time to also formulate some natural open problems in this area. But again, let us postpone this for the future. Thank you.
Thank you.
Okay. Okay. We can finish it.
We will have the time.
Okay. Okay. The time is over.
Yes.
Thank you very much. Okay.
Thank you.